Xin Yu. He's currently a postdoc at Stanford. Graduated from New York University in May 2005. And today she's going to present his work.
Good afternoon, everyone. The topic of my thesis of this talk is mobility, routing cache, and TCP performance in ad hoc network. A mobile ad hoc network is multi-hop wireless network. In such network, there is no fixed network infrastructure. Nodes can move arbitrarily and cooperate to forward packets to each other to enable communication between nodes that are not within wireless transmission range. For example, node A cannot communicate directly with node C, but they can talk to each other through node B. There are three fundamental differences between ad hoc networks and the wireless network. They are limited bandwidth, scarce energy because nodes are generally powered by batteries, and frequent topology changes due to mobility. There are many promising applications of ad hoc networks. For example, emergency disaster relief, military communication, and sensor network. More recently, there are wireless mesh networks that is a kind of ad hoc network. Mobility presents a fundamental challenge to routing and transport protocols. Now I give a brief overview of routing protocol for ad hoc networks. Routing protocol for ad hoc networks can be classified into two main types, proactive protocols and reactive protocols. Proactive protocol attempt to maintain up-to-date routing information to all the nodes in the network. In such protocol periodically propagates topology updates throughout the network. Therefore, they introduce significant overhead. An example of proactive protocol includes DSGV, OLSR, and TBRPF. In contrast, on-demand protocols discover routes only when nodes wants to send a packet to a destination. A source node will broadcast a route request. When destination receives its request, it will send reply to the source. To reduce the overhead and latency of such network flooding, on-demand protocol generally use route caches to cache discovered routes for future use. Examples include DSR and AODV. In my thesis, I focus on DSR. In on-demand protocols, due to mobility, cache routes can easily become stale. Since nodes use cache route to respond to route requests, stale routes can be quickly propagated to other nodes. Using stale routes can degrade performance of routing protocol. It can cause packet losses if an intermediate node cannot salvage a packet. It can increase delivery latency due to very expensive link failure detection. It can also increase routing overhead because the node detecting broken link needs to send a route error to the source node. So the first question I investigate in my thesis is how to make on-demand protocol adapt quickly to topology changes. Now I give a brief overview of TCP. TCP provides reliability through positive acknowledgement with retransmission. This technology requires TCP receiver to send an ACK to the sender when to receive data. When the sender sends a packet, it starts a timer. If the timer times out and the sender has not received an ACK, the sender will assume the packet is lost and retransmit the packet. To make transmission more efficient, TCP uses technology called sliding window. Sliding window allows TCP to send multiple packets before waiting for an ACK. To avoid congestion, TCP maintains a second limit called congestion window. Congestion window limits the amount of data TCP can send. For example, the congestion window size is 8. When TCP receives an ACK for packet 1, the window will slide and the TCP sender is allowed to send the packet 9. TCP assumes packet losses occur because of congestion. It detects congestion through timeouts or through duplicated acts. In case of congestion, TCP will reduce congestion window size to one packet, double retransmission timeout, and inter-slow start phase. It is well known that TCP performance degrades significantly in ad hoc network because most packets are lost in ad hoc network because of route failures rather than congestion. Since TCP cannot distinguish the packet losses caused by mobility from those caused by congestion, it will falsely trigger congestion control. For on-demand routing protocol, due to slow routes, TCP can experience repeated timeouts. So the second question I investigate in my thesis is how to make TCP efficient in the presence of frequent packet losses. The first contribution in my thesis is to address the cache stillness issue in on-demand routing protocol. I define a new cache structure called a cache table and design a distributed cache update algorithm. I show that proactive cache updating is more efficient than adaptive timeout mechanism. Second, I propose to improve TCP performance by exploring cross-layer information awareness. I show that it's important to make a routing protocol aware of lost TCP packets and help reduce timeouts. I designed two mechanisms to improve TCP throughput, early packet loss notification, and best ever act delivery. Finally, I studied the impact of caching strategy on the scalability of on-demand routing protocols. In this talk, I will focus on the first two parts of my thesis. Next, I will introduce the distributed cache update algorithm for DSR. Now I show an example of DSR and how routes are cached in DSR. Source node A discovers route to destination E. Its broadcast route request includes its own address A. When B receives this route request, it will add its own address to the packet and rebroadcast. Since here we assume that B does not have a cache route to destination. C will add its address to the packet and rebroadcast. D will do the similar thing, and when destination receives the packet, it will send route reply to A. When D receives this packet, it will cache the downstream link DE because this link has been confirmed to be bidirectional by the MAC layer. C will cache downstream link CBE, and B will cache DCE. A will cache the full path. Now A starts to send the first packet. When B receives the packet, it will cache the upstream link DA as a separate route. This is the path cache used in DSR. C will cache upstream link CBA, and D will cache DCBA. E will cache the full path. Now we assume that source node F initiates route discovery to H, and so F caches the full path. G will cache both upstream link G, F, and the downstream links. We assume K initiates route discovery to G. This G and has not transmitted data yet, so node G only cache downstream links. C will cache DDG and D will cache DG. G's cache is empty because no data packet has been transmitted yet. I designed the cache route to be of three types: proactive, active, and post-active. Preactive route means the route has been discovered but has not been used. Active means the routes are currently being used, and post-active means the route was used before but now is not. In DSR, when CE is detected as broken, C will send route error to source node A. Each node forwarding this route error will remove route containing a broken link. This process is called on-demand route maintain. As we can see, on-demand route maintain removes still routes only from upstream nodes. However, both upstream and downstream nodes on post-active routes and all upstream nodes on pre-active routes have also cached the broken link. FJCDH is a post-active route and TJCDJ is a pre-active route. This is a cache stillness issue. Therefore, we need to address this problem. To address this problem, prior work mainly use adaptive timeout mechanism. Such mechanism use heuristic to predict the timeout of a link or route. For example, link MATLAB for DSR, it estimates timeout based on observed link breakage and usage. There are two limitations. The first limitation is heuristics cannot accurately estimate timeout because topology changes are unpredictable. The second limitation is such mechanism generally use ad hoc parameters. Such parameters work well for certain scenarios, but may not work well for other scenarios. Moreover, in the real-world scenario are different from those using simulation. As a result, if timeout is too short, valid routes will be removed. If timeout is too long, still routes will be kept in caches. My proposal is proactive cache updating, which means proactively disseminate the information about broken link to the nodes that have cached that link. Proactive cache updating is key to make route caches adapt quickly to topology changes. It's also necessary to notify only the nodes that have cached a broken link in order to avoid the overhead of notifying other nodes. There are two challenges to achieve this goal. First, how to know which nodes have cached a broken link. Second, how to notify those nodes efficiently because of mobility and the fast propagation of route information. My solution is to keep track topology propagation states in a distributed manner. The topology propagation state means which node has cached which link. I define a new cache structure to maintain the information necessary for cache updating. Each node gathers such information during route discovery and data transmission without introduce additional overhead. I design a distributed cache update algorithm. This algorithm uses local information kept by each node to achieve distributed cache updating. When node detects broken link, it notifies the neighbors that have cached the link according to the information in its cache table. When the node receives a notification, it in turn notifies its neighbors according to the information in its cache table. Therefore, the algorithm can quickly disseminate the notification to all reachable nodes that need to be notified. Successfully deliver the packet to the next hop, then downstream nodes will quickly cache the first downstream link. Otherwise, the downstream nodes will not cache the first downstream link. This is the way how nodes gather the information. Data packet field is used to record whether node has forwarded 0, 1, or 2 data packets. I will show example for this in the next few slides. The second field is reply record. It records the information to which route reply is forwarded and the downstream links that neighbor have learned. Here's the example. Source node A wants to discover to destination E. E sends a route reply to A. When D receives this route reply, it will cache downstream link DE. This is the same as done in DSR. In addition, we keep 3 additional fields: source and destination pair AE, data packet 0 because E has not forwarded any packet for source node A, and the fourth field is called reply record. it requires that C will learn link DE. When C receives this packet, it will create a new entry requires the downstream link CDE data packet 0, and B will learn link CDE. Then C will send a root reply to B. And B will also add a new entry require the downstream link, and the neighbor A will learn link BCDE. A will cache the full path. Now A begins to transmit the first packet to E. E will update the data packets from 0 to 1, and when B receives the first packet, it will make 3 changes. The first change is to remove the reply record entry in which the concatenation of the two fields is either the full path of source root or the subroot or the downstream node of the source root, and update data packets from 0 to 1 because B is forwarding the first packet, and add upstream links to the root consisting of the downstream links so as to complete a full path. The reason we remove the reply record is because according to the complete path, the nodes will know that A and B have cached the downstream links. Therefore, the information in the reply record entry is redundant. C will do similar thing, complete the full path and remove reply record and update the data packet. E will cache the full path. I will show why we need to keep the data packet fields is 0, 1, or 2 when I talk about the algorithm. Now, this part I only explain how the information is gathered. When another example, when F initiates root discovery to E and C receive a root request from G, C will extend its cache table by adding G will learn link CDE, and when G receives this root reply, it will add an entry and record that F will learn link GCDE. Then G will send a root reply to F. There are 4 desirable properties of the algorithm. First, the algorithm is fully distributed, which means the algorithm uses only local information kept by each node and communicates with its neighbors. Second, the algorithm notifies only the nodes that have cache broken link. Third, the algorithm combines the advantage of proactive and reactive protocols. That is, on-demand link detection and proactive cache updating. Finally, the algorithm does not use ad hoc parameters. Therefore, it makes those caches fully adaptive to topology changes. As we have shown, the goal of the algorithm is to notify all reachable nodes that need to be notified. The algorithm starts either when a node detects a link failure or when a node receives a notification. In either case, it checks each entry in its cache and produces a notification list. Each entry in this list includes a node to be notified and a route to reach that node. I define a broken link to be a forward or backward link. Here's the example. When C detects the CD is broken, CD is a forward link for route HICDA, but it's a backward link for route ABCDE. The operation of the algorithm for these 2 types of link is symmetric. The algorithm consists of 2 paths. In the first path, a node detects broken link. It checks each route. If a route contains a forward link, then it checks the data packets. If the field is true or 1, then upstream node needs to be notified because this node has received at least 1 data packet. Therefore, upstream nodes have cached downstream links, including the broken link, immediate next hop downstream link.
Sorry to interrupt. Could you go back one step, please? So just so that I understand this, there is you maintain the complete path in the cache from A to E.
One of the intermediate node has cache route to reach TCP sender. Then the receiver will check the cache to see whether it can reach the sender or not. If the receiver does not have route to reach the sender, then it's just drop the notification.
So I have a question about this slide. So do you mean that in the case that C does not have a cache around reach to A, all the TCP ACK frames will drop in C.
Sorry.
All the TCP acknowledgements will drop in C. In this case?
If C does not have a cache route to A, it will send notification to the receiver.
You send a notification to E.
Yeah.
And then E will resend the TCP acknowledgement to D. Do you mean that?
No. C will send notification to E. When E receives this notification, it will check whether, because I set a flag in the notification, that flag indicates whether an app has been retransmitted for that connection or not. If that app is not set, that means none of the previous nodes have retransmitted app. Then E will check its cache to see whether it can send app or not. If E cannot send this, it will forward notification. If E can retransmit, it will reset the flow to indicate that an app has been retransmitted, so that following node will not retransmit an app.
My question is that in the case that D, so whenever D have already finished whenever D have already transmitted the packet TCP acknowledgement to C, D will not have the packet again. So D cannot retransmit to K unless E send another TCP packet to it. Right?
C only send notification.
Yes,
So does D
but D does not have a
maintain,
packet to send.
does D cache all the apps that it has forwarded?
No, D does not cache anything.
So how would it write the app to retransmit?
It generates new packets. Generate
So it maintains per flow state information.
does not contain per flow.
So how does D have
Because in the notification I set a variable whether indicates the variable indicates whether an app has been retransmitted for the lost app. If C has retransmitted the packet, then the flag will be set so that
So the notification has the information for D to regenerate the app.
yes, notification includes the information whether app has been retransmitted or not. So here you see E has retransmitted app, therefore it's set that variable so that E will know E does not need to retransmit. Just the information is in the packet. Each node does not maintain any additional state.
So actually the question is like this. So C sends the notification to D, right? Then in that case, because D has a alternative route, so D needs to resend the acknowledgement. So I think his question is asking, how does D know which packet to send to A?
The notification. Okay.
So does the notification have enough information for
Yes.
D to regenerate this packet?
Right.
Okay.
So D regenerate this packet from cache or somewhere.
No.
From
the
notification act number.
From notification.
Notification has the act number, sequence number.
So if the app TCP packet is some peak load with some data packet,
Right.
so the D cannot generate the peak load with the data information.
No. There is a key point here. Why we cannot do this similar thing for data packets? Because data packets includes the big information of all those data. We cannot regenerate the data packet. Here, why we can do this? Because we only need the 6th number of the app. Also,
So
there is
D actually always generates the TCP header.
yes, TCP header and the 6th number of the app. The highest 6th number, because we only need the highest 6th number for that connection. So he just put the 6th number so that we will know how many packets have been received so far. So there's no additional information. That's why that is a solved bug. Both EPRN and bit only explore cross-layer information aware, that is, a network layer is aware of TCP information. There is no cross-layer information exchange at intermediate nodes, but there is cross-layer interactions at the TCP sender. We freeze TCP upon rough failures as ERFN, and the network layer will notify TCP about each lost packet when they receive EPRFN notification. TCP will record all those lost packets and retransmit the packets with a low sequence number. When to receive ACK, TCP will restore congestion control and transmit other packets. The reason is we transmit only the low sequence number packets is that because the root can be stale, so it's better to wait for ACK before sending other packets. Here is TCP throughput for 100 nodes and 10 TCP connections. This is the ERFN, the DSR under promiscuous and non-promiscuous mode. The higher line is the DSR with promiscuous mode. These two lines are ERFN, EPRN bit, and the DSR with pass cache. Then this, the green and the red line are ERFN, EPRN bit, and DSR updates. As we can see, both EPRN and bit with pass cache and the cache update algorithm outperform ERFN. Also, EPRN and bit with DSR updates performs better than with DSR pass cache. The reason is because when we use the algorithm, the cache is much better than DSR with pass cache. Therefore, it can EPRN can send more notification and bit can retransmit more ACK, contributing to better performance. Also, these two mechanisms perform much better on the higher mobility because on the higher mobility there are more route failures and more packet losses. This is the results for 50 node and 1 TCP connection and the number of slow starts. As we can see, the two mechanisms significantly reduce the number of TCP slow start, therefore it significantly reduce the timeout. These are related work at MAC layer, network layer, and transport layer, as we have shown that the pre-work merely to notify TCP about link failure. In my work, I focus on handling both data and ACK losses. Conclusions. I have shown that proactive cache updating is more efficient than adaptive timeout mechanism. Proactive cache updating is key to adaptation of on-demand protocols to mobility. I have presented two feedback mechanisms, EPRN and bit. These two mechanisms are applicable to any routing protocols. Cross-layer information awareness is key to making TCP efficient in presence of mobility. Finally, it's important to make routing caches adapt quickly to topology changes because the validity of cache routes not only affects TCP performance, but also the effectiveness of mechanisms used to improve TCP performance. Thank you.